But so here's what I want to say again about all of these exponential growth, exponential decay problems. They're almost all the same in that they're always giving you, even though it might seem really hidden, they're always giving you two data points, two pieces of information, and then they're usually asking you to find out something else at some third point. So they're giving you some time and some amount, some other time and some amount, and then asking you, how much do you have at this time? Or what time is it when you have this amount? That is always the kind of setup. So if you can kind of recognize that and write down the data in a meaningful way, it's going to be easier to kind of figure out what they're really asking for. Also, once again, for those of you that just walked in, if you need to fill out the attendance form, I forgot to bring the code. So you'll need to go to the Canvas, to the modules. It's the first link in the modules. All right. So let's look at something similar to number 3. I'm going to make it a little harder because why not? So section 4.6. So let's say we have the following. After 4 years, 90%, it's very slowly decaying. Not really. No, that's not that slow. Of the initial amount of a radioactive substance, blah, 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 blah. And we don't really need to read all these words. Substance remains. What is the half-life of said substance? Okay, so the percentage ones are seemingly more annoying because they're actually not giving you any amounts, but that's actually the best case scenario. So if you have one that's a percentage where they haven't told you you're starting with 52 grams of material, you should be like, yes, I'm in luck. I can make the numbers easy because you can start with whatever amount you want. And you should start with, if you're dealing with percentages, how much? 100. You can also pick 1, you can also pick C, but to me, it's easiest if I pick 100. But really, you can pick any number that's going to work nicely for you. So I'm going to start with, and so what I actually say is, I'm always going to make this little table of times and amounts. And of course, I'm doing this with the thought that my model is, of course, always the model for exponential growth or decay, y equal to c e to the kt. It's always what we're doing. So whenever you have these exponential growth decay problems, your job always first is to find c and k, typically in that order, but not always. Sometimes you do find k first and c second. And then after you find C and K, you'll have the actual model where you know what things are, and then you can find the thing they're actually asking you to find. All right, so let's see what we've got. After 4 years, 90% is left. So at the beginning, at time equals 0, you have 100% of the stuff. You can think of it as 100%, you can think of it as 100 grams, you can think of it as 100 tons, 100 of whatever units you want, right? They didn't give us units, we don't have to use them. And then 4 years later, we have 90% of 100, which is 90. That's why I picked 100, because percents are really easy. One thing to be careful with, sometimes, not here, but sometimes they like to make this trickier by making it a language problem and saying the amount that's decayed. It's decayed. Someone could write the same question, but say instead of 90% of the initial amount remaining, they could have said the initial amount decayed by 10%, meaning you lost 10%. But the function always talks about how much you have. They might also use really not nice language and say decayed to 90%, which would mean you still had 90%, but they're just using language to make it extra confusing. So really, really, really be careful when you're reading this. You always want to be thinking about, I am writing down how much I have, not how much I've lost. Okay. And then finally, we have the 2 data points. And then the third thing is going to be, we want to know something when something is true. Here we want to know the half-life. What does half-life actually mean? It's an amount of time. So we're looking for the time it takes for half of it to be, I always think of it as for half of it to decay, but it's also equally correct to say for half of it to still remain. So the amount of time it takes to go from some amount to having just half of that amount. To have half of what you had. So in our table here, that means we are going to want to figure out how long it takes. We don't know. We're trying to figure out the time until we get to what value? 50. Now, I will say, I've heard people in the past say 45 when I've written it like this because they're thinking half of 90. But you really want to be, and you could do it that way. You just have to work harder to do it that way. The way you should do it is always half of like your beginning amount. Although really you can think of it as half of end. So if you did 45, it would be the time from 4 to whatever you got. But that's not how you should do it. All right, so the rest of this is plugging in the numbers and finding the things. I think I'm thirsty. I think that we're at a point where we should be able to say that we know that if t equals 0, the y value is just your c value, right? If your initial value, your beginning population, whatever you want to call it, that's what you're going to get when you get t equals 0, and that's what's going to be c. You could also plug it in, right? If you plug in 100 for y and 0 for t, oh yeah, k times 0 is 0, e to the 0 is 1, c times 1 is c. So that's going to give you c equal to 100. Great. So we used this piece of data, check. Now we're going to use the other piece of data. Also substituting in our new value of c, right? You want to use all the things you have as you get them. So now our model has been updated. It's going to be 100 e to the ket. And then we're going to plug in this new piece of data, or this other piece. It's not really new. We're going to plug in 90 equal to 100 e to the k times 4. And then we're going to solve for k. And it's usually not going to be very pretty. But you really shouldn't use a calculator to get a decimal approximation. You really kind of have to leave it as its unnice form, as whatever it is. Solving for this, I'm going to divide both sides by 100. So 90 divided by 100 is 0.9, or 9/10 if you prefer a fraction. Usually I prefer a fraction, but not when it's so easy to divide by 100. So 0.9 equals e to the 4k. Then we take the natural log of both sides. So natural log of 0.9 equals 4 times k. And then we divide both sides by 4. In your homework problem, I think you just have a 1k there, so it's going to be even nicer. K is just going to be the natural log of whatever. So there's our k value. Natural log of 0.9 divided by 4. And now we update our model. So our fully fledged final model is y equals c, which is 100, times e to the k, which is natural log of 0.9 over 4 times t. Sorry, that's a little close to that. Just as a throwback from something I think I said a couple classes ago, sometimes people, web work, professors, like to write this as y equal to 100 exp of natural log of 0.9 over 4 times t. Just a reminder that exp just means e to the power of. I've seen some of you have seen that notation already in web work, so that's what that is telling you. I guess it's a way of not having to try and stuff all this stuff up actually in this superscript. So it's somewhat nicer, right? We've got the model. We still have to answer the question. So the question was, what is the half-life? Well, the half-life is when we get down to half of what we started with. So we're going to set y equal to 50. So we're going to plug in 50 for y, and hopefully we have enough room here. So 50 is going to equal 100 e to the natural log of 0.9 divided by 4 times t. Sorry if that's getting a little smushed in there. You guys can see that all right, right? Yeah, it looks all right. Okay. So I should say, typically, after you solve for k, if the next thing you're doing is then solving for a different time, it's practically the same process as solving for k. You're going to divide by the coefficient, then take the natural log of both sides, then isolate k. So I'm going to divide both sides by 100. I'm going to get 1/2. Not surprisingly, when you're finding the half-life, you typically get a half on the side after you divide both sides or whatever, equal to e to the stuff times t. And then we take the natural log of both sides. The natural log of 1/2 equals, and now this is where I'm going to encourage you to remember, the natural log of e to a thing is just the thing. I don't want to write natural log of e to the natural log of 0.9 over 4 times t. I just am going to know that the natural log of e to the stuff is just the stuff. Natural log of 0.9 over 4 times t. And then I would encourage you all to, instead of, we don't want to write the answer, or at least I don't want to write the answer, as the natural log of 1/2 divided by natural log of 0.9 over 4. I want to instead multiply both sides by 4 and get 4 times natural log of 1/2 and divide both sides by natural log of 0.9. That is, in my opinion, the best way to write this answer. Oops, except I meant to circle the t there. Oh, sorry. Okay. And you do need to enter your answer into WebWork like this. It is not going to be happy if you try to give it a decimal approximation. It will probably not accept it. Very occasionally, if you write enough decimals, sometimes it will. But in my experience, you need to write the exact answer, which is that. Just like if your answer is square root of 2, you don't want to write 1.41. You want to literally write in square root of 2 or 2 to the 1/2 power. So, yeah. Questions about anything we've done here before we do a couple more?
I have sort of just, this is a basic question, but for some reason when I do this, I get really confused about the variables, which is that t is time.
Correct. And that is the, well, I would say that and y are the only variables.
Right, okay. But it's trying to articulate why it's confusing. Our final answer is t equals that.
Right, because the question, because what was the thing they were asking for?
Or what is the half-life?
Right, they're asking for what is the half-life? What is the amount of time it takes for half of the stuff to dissipate? But in other times, but in other questions, they might ask you how, like, after so many years, how much stuff do we have? So yeah, usually there's this whole process of finding the constant C and K and then having to actually answer the question. And the question is always going to be, if it's how long does it take to do something, or after some period of time, how much do we have?
Okay.
Those are the only really, I mean, you can make up other terrible questions if you really try, but really those are the only two kinds of questions we can ask. How much stuff do you have at a certain time, or what time is it when you have a certain amount of stuff? It's kind of it. So I really want you to all to see this process where you write down like these two columns, 3 entries, one of them has an unknown somewhere. This kind of process typically works for almost any of these exponential growth or decay situations. You can always do this. So we're going to make up one together here. Well, I'm going to make up one, and I'm going to ask you all to kind of write down the information in the column. And it'll be similar to problem 4 here, but I'm going to make up a different element. So let's see. Let's say here. So let's see. Radioactive. Oh, radioactive. Start singing that song. No, okay, don't. Radioactive. Let's call it parmentonium. My favorite element. Has a half-life of 888 years. What percent will remain after, let's say 300 years? And before you write anything down other than what you've already written, I want you to think about some number sense kind of stuff for a second. If it takes 888 years for half of it to dissipate, so you're starting with some amount, 888 years, half of it would be gone, half of it would be left. If I'm asking how much is going to remain after 300 years, or what percent is going to remain after 300 years, is that percentage going to be larger than 50% is going to remain, or less than 50% is going to remain? If I'm going 300 years. Well, yes, give me a thumbs up for larger, give me a thumbs down for lesser. Yeah, right. It's going to be more than 50% because I haven't gone long enough to have dissipated that much. So it is good to think about what things are going to be. To that end, when I make my little table of amounts and times, I like to try to put the times in order. So if I was doing this one, I would put the times in order as, well, what's the first time you're going to put in your table? 0, right? We're going to put time equals 0, and you're going to have what percentage? Right. Okay. I want you all to fill in the table. You should have 3 rows worth of information. One of those rows is going to be missing something. I think I'll look around and see. like, of all the things you can do to make this easier, I think this is the one thing that's really going to make keeping problems easier. So get this down, you can bring all that. So we have time equals 0 and we have 100%. And then what time is it when we have, well, actually, what percent do we have after 888 years? 50. Right, that's the half-life, that's how much we have. And then, okay, so the thing is, you could put 888 in the next time slot, but I know 300 is also a time I'm going to do. So if I'm going to write things in order, I'm going to put 888 down at the bottom just so I can make it more in order. It's not necessary. You can really do whatever you want, but that's what I'm thinking. So I know that after 888 years, I'm going to have half of what I started with. And then I know the question I'm asking is, after 300 years, I want to know how much I have. Specifically, what percentage? So whatever number I get for my answer, that'll be the percentage. And did not think ahead. Oh well. Didn't bring a calculator, so we won't actually get to see what the number is approximately, but whatever. Okay, so it's the same work. Literally, we're going to do the same thing we did last time. The only real difference is at the end, we're going to plug in something for time and solve for y instead of plugging something in for y and solving for time. But that's kind of the only real meaningful difference here. So again, we see that C is going to be 100. Right? I don't think we need to show the work for that. C is 100. I want to emphasize that's only true if you're starting at time equals 0. Right? There's another problem. I think it's problem 2 in this, where you're given points like 1, 7, and 4, 16, and has to find C and K. And C isn't 7. It's not the value you get when you plug in the first thing. C is only the value you get if you plug in 0. And if you don't have 0 to plug in, it's a harder process to find C. Okay, so then we have y equal to 100 e to the kt. And now we're going to plug in the other point of data. We're going to plug in that y is 50. In fact, and time is 888 years. And I prefer to write the number before k, but it doesn't really matter. So then we solve for k just like we did the last time. We divide both sides by that coefficient. So 50 divided by 100 is equal to e to the 888k. We reduce that fraction to 1/2, which I should have done right there. And we take the natural log of both sides. So natural log of 1/2 equals 888k. So then we solve for k, and we get k equals the natural log of 1/2 divided by 888. If you've ever taken chemistry, you probably recognize that this is how you typically find k if you know the half-life, or the half-life if you know k. So just something worth knowing on the side, although you probably still have to show your work. It is true that the half-life is always going to equal the natural log of 1/2 divided by k. Or alternatively, k is always going to equal the natural log of 1/2 divided by the half-life. You might have seen it as natural log of 2 because someone was saying something else was negative when it was really positive or whatever, but it's the same idea. So then we go back and we plug this in to get our fully fledged model. So our model is going to be y equal to 100 e to the this times t. Natural log of 1/2 over 888 times t. The nice thing about these questions, when they're asking you to find how much stuff you have after a certain number of years, is it's a one-step process. You plug in t equal to 300 and you're done, because you don't have to do any solving for t. You've already got y isolated. So plug in t equal to 300. And we're going to get y equal to 100 e to the natural log of 1/2 over 888 times 300. And as I said before, you should enter your answer into web work like this. You don't want a decimal approximation. I will point out, because you might have learned this a different way once upon a time, you might not have. There is a way to write this a different way. And I feel like I should show you just so if you have seen it this way, you can justify to yourself, oh yeah, it is the same as the next cycle. So technically, if you really, really wanted to, you could write this as 100 e to the, check this out. I'm going to say I have 300 over 888 times the natural log of 1/2. And when you have a number times the natural log of a thing, that number can come up as the power of the thing in the natural log, meaning this 300 over 888 can be the power on 1/2. So we could write this as 100 e to the natural log of 1/2 to the power of 300 over 888. But then e to the natural log of a thing is just a thing. So you could really write this as 100 times 1/2 to the power of 300 over 888. Now let me point out how this makes sense. We plugged in 300 to find the amount, right? I didn't find the number because I didn't bring my calculator, and I don't want to do this on my phone because it'll be stupid. But let me ask you a different question. What if instead of plugging in 300, we had plugged in 888? What would we have as our power there? What's 1/2 to the first power? And I'm asking easy questions. What's 100 times 1/2? Which is how much we should have after 888 years. So it makes sense. In fact, some people totally teach exponential growth and decay this way, where you say like the half-life is kind of the thing that becomes your base. If you don't like this, ignore it. You don't have to, and your teacher probably has not taught it this way. But this is another way people do this. It's a perfectly valid way of seeing how exponential growth or decay works. Because the half-life or the doubling time are kind of things that actually really matter. So the point of doing this, aside from saying that, is also that if you really wanted to, you could type this into web work instead of typing this into web work. Is this better? Yeah, maybe. Maybe not. Yeah, I kind of want to know what it is though. So, oh, thank you. Okay, what is it? 79.12. Okay, that seems about right. So the answer to this is this percent, which is approximately 79.12%, which certainly corresponds to our thought that it should be more than 50%. Okay. Questions about this? I keep hiding this from myself. It's like right there. Okay. Let's look at number 5, and then unless we want to do more, we'll move on to more antiderivatives. Okay, so for number 5, or one similar number 5, I'm going to say the same things I said for the last 2. It's still going to be a process of having 1, 2 data points, and then there's going to be a third thing where they tell you one thing and you have to find the other thing. It's always the same sort of thing. I'm going to use the one that's actually on my printout here because why not? So here's what I've actually done. I'm not going to write down all the words. I'm going to read the words and write down what's pertinent. So let's see what we've got here. Because of an economic slump, I don't need to write that down. The company finds that its annual profits have dropped from $500,000 in 2006. Okay, so profits were $500,000 in 2006. And then the profits were $100,000 in 2009. And then they want to know what's the expected profit. I'm going to change that to a different year. That's not exciting. I want to know so again, assuming a model of exponential decay, which is always what we're doing if we're doing these exponential growth and decay problems, right? They'll either say words like if profit follows an exponential decline, or they might say something dumb like if the rate of growth is proportional to the population size, which is another way of saying you've got exponential decay. You'll probably see that actually more in 16C if you take 16C, when you talk about differential equations, that is something that comes up. But here they're saying if we have exponential decline, what's the expected profit in, I'm going to say 2011. Okay, and so they give us a hint though. They give us a hint, which I don't think we don't even really need the hint, because I think it is a reasonable expectation that we should know that if you're given things like this and time measured in years, you want to make the starting year time equals 0. So we're definitely going to make 2006 time equals 0. And then 2009 is going to be time equal to what? Right. And then 2011 is going to be time equal to 5. So let's make our table. Just like every other time, we have the same sort of thing. Two known data points and one where we know one thing and one find the other thing. So everybody should be able to tell me if we have y equals c e to the ket, what's our c value? 500,000, right? Whatever you got at times 0. Okay, I want everybody to now start with y equal to 500,000 e. Oh, so this is where I've done something slightly dumb, but not that dumb. If k is one of the constants I'm trying to find, even though I know 500k means 500,000, it's probably a bad idea to write down a different use of k. So I'm going to change this back to just 500,000 so it doesn't look like I've got k's all over the place. Try not to use the same letter for different things if you can help it. I was doing that there. So I want you all to start with y equal to 500,000 e to the kt, and I want you all to solve for k. So use that second data point, plug in for t and for, oh, I used y here. I guess I should have used p because I called it p. Sorry. I called it a different name because I wanted to, because p made sense for profit. So I want you all to use the t equal to 3 and p equal to 100,000 to solve for k. That's what you should get for k. Oh, okay, so that's fine. I'm like, that doesn't look right. Okay. Yeah, that's always going to use your own number, doesn't my numbers. So where'd the pen go? So we're plugging in 100,000 for p and 3 for t. And then, oops, I forgot to write the e to the k times 3. That's terrible. Sorry, making mistakes. Okay, so then we divide both sides by 500,000. 100,000 divided by 500,000 is 1/5 equals e to the 3k. We take the natural log of both sides. So natural log of 1/5 equals 3k. That is a 5, believe it or not. And then finally divide both sides by 3. So the natural log of 1/5 over 3 equals k. That is as simple as k gets, right? You can't say it's natural log of 1/15. You can't say 1/5 divided by 3 because that 3 is not inside the logarithm. So be careful. Don't be making those kind of logarithmic errors. And then finally, we're going to write our model. So our model is p equals 500,000 e to the natural log of 1/5 over 3 times t. And then we're going to plug in time equal to 5. That would have been a better question. Oh, well. We're going to plug in time equal to, that'd be interesting. We're going to plug in time equal to 5 to find out what it is. So it's going to be 500,000 e to the natural log of 1/5 over 3 times 5. And that is how much profit we'll expect to get in the year 2011, whatever that number happens to be. And again, just to kind of see here, I want to see one thing. Yeah. So I will point out, that's kind of interesting. So this is my answer. This is the number of dollars that I expect to be profit in the year 2011. But the question asks you for expected profit is blank $1,000. So if I write this number in there, that's not right, because this says 500,000. Let's pretend this answer ended up being like I don't know, let's pretend it ended up being $80,000. Let's say that this was I don't know what it is, I'm just making up numbers. I know it's less than 100,000. Let's say it's like, let's say it's $36,000. The problem is if I write $36,000, it's not what they want. If this is my answer, they want me to write 36. So if this is my answer, because I can't write, I don't want a decimal approximation. If this is my answer, they don't want me to write this. They want me to write 500 e to the natural log of garbage $1,000. Right? That's what's going in the blank. It's kind of annoying. But if you know that the amount you're getting is in dollars and you want it, and they're asking you to write it in thousands of dollars, you have to divide your answer by 1,000. I suppose the other way we could have avoided this garbage in the first place is by realizing that they were doing it in $500,000. So instead of writing this, I could have just said another way of doing this. So just to kind of, we could have said instead we have profit in thousands of dollars. So then our numbers could have been, instead of 500,000, just 500, instead of 100,000, just 100. And so then when we had done this, we would have ended up with a 500 here instead of a 500,000. That's probably the better way to have gone about it. I just didn't see that till the very end. So it's usually a good idea to look at how they're asking you to answer the question and to try to write your number using their numbers using those measurements. So if they're asking for an answer in thousands of dollars, it's good to write your profit in thousands of dollars. So the beginning profit was $500,000. Next profit was $100,000. Not too bad though. So, okay. What time is it? We got 15 minutes. Okay. Other exponential growth decay questions before we move back to talking about antiderivatives. Yeah. Sorry, which one? Okay, so I'm gonna say two because one is a lot easier than two. But so we'll look at both. Let's look at both. They're not too terrible to do. So let's say, so this is where we're looking at the function y equals c to the kt passes through 2 points. And so the difference between 1 and 2 is that for 1, you have y equals c e to the kt, and one of the points is 0, something. And the second point is something else, 6, 23. Once again, I guess you don't really need to make, you could make a table here, but the table here, they're not asking you to do a third thing. So you don't really need the table, although I still like the table to know what's what. So in my table here, t is 0, y is 9. And then from this point, t is 6, y is 23. That just helps me keep track of where I'm putting things. It's good to know what you want to do. So for this one, finding c is still a straightforward process. We can find c by just plugging in 0 for t and getting y equal to 9. So sorry, c, well, y, which will be c. But let's do it. So I plug this in. I'm going to get 9 equal to c times e to the k times 0, which is going to give us 9 equal to c. So then we have y equal to 9 e to the kt, and then we plug in the other data point, and we get 23 equal to 9 e to the k times 6. And then we solve for k. So divide both sides by 9. Take the natural log of both sides. And finally, k is going to be the natural log of 23 over 9, all divided by 6. Which is not particularly lovely, but it is what it is. So those would be our answers here. So when one of the points has t equal to 0, it's basically the same as what we've been doing for these other problems. The other example is a little bit harder. So let's look at something similar to problem 2. So let's say we have, again, the same sort of setup, y equals c to the kt, but now the points are something like, I don't know, 3, 8, and 7, 31. Gross numbers. Okay. So when this is the situation, you can't just plug something in and get c right away. right? If I plug in 3, look what happens. I get, well, I guess make my table because table's good. I like the table. I'm not gonna lie. Table's where it's at. There's my table. Okay, I know what's going where. So if I plug in the first set of data points, I'm going to get 8 equal to C e to the k times 3, or I'm going to write 3 times k. I don't know what C is, right? I can't just say C is a number because I still have a k in there. And if I plug in this other data point, I'm going to get 31 equal to C e to the 7 times k. There are 2 equally good ways to go from this point. I should have written these in the other order though. Oh well. So I'm going to rewrite these just slightly because there's a nicer way of doing this. So one way of doing this, which I think a lot of people have seen, is to take these equations, 31 equals C to the 7k and 8 equals C to the 3k, and to divide them by each other. So it is true. So I just want to point out something that's going to sound kind of dumb, but it's totally true. I have a pen in here. Oh, I brought pens. It was once finally smart pens. So I just want to say something that is going to maybe sound a little bit dumb. Definitely 2 to the 5 equals 5, right? Sure. And 3 equals 3. Yes, you agree? Yes, you agree. And then if you divide this side by this side and that side by that side, if you divide equal things by equal things, the division is not surprisingly equal. So, but it's true whether you know the exact numbers or you just know the things are equal to each other. So it is definitely true that 31 divided by 8 is equal to C e to the 7k divided by C e to the 3k. But the nice thing about that is that we can cancel the c's, and e to the 7k divided by e to the 3k, we can subtract the powers and say that, well, that's e to the 4k. 7k minus 3k at 4k. And then we can solve for k. So if we do that, we can solve for k. We get the natural log of 31/8 equals 4k. And then k is equal to 1/4 natural log of 31/8. Or if you prefer, natural log of 31/8 all divided by 4. But we're not done. We still have to find c. So to find c, take either one of these equations, it doesn't matter which one, and solve for c. So we take this first one and solve for c, we get 8 divided by e to the 3k is equal to c. And then substitute this in for k. So it's not going to be lovely, but c is going to equal 8 divided by e to the 3 times all that. I would probably look at this and say, oh, 3 times 1/4 is 3/4. So I would say I'm going to have e to the 3/4 natural log of 31/8. Or if you use the other one, you would have c equal to 31 over e to the 7k. And if you plug that in, you would get c equal to 31 over e to the 7 times all that. So 7/4 natural log of 31/8. And I promise you, these numbers are exactly the same. They don't look very much the same, but they are exactly the same. Kind of bonkers that they're exactly the same, but they are. The other way of solving this is to take these two things that we solved for C and to set them equal to each other to solve for K. If you do that, you'll end up getting back to here. So just to point that out, because I do think it's worthwhile to see because that, to be honest, until I had seen someone do it this way, I had never thought of dividing these things by each other. This just wasn't the way my brain ever wanted to do it. I was like, well, what do I got? I've got something here. I can solve both of those for C, and I can set them equal to each other. So I set them equal to each other. Here's what happens. So let's see if I set, what do I got here? 8 over e to the 3k equal to 31 over e to the 7k. Let's see what happens. Well, I want to solve for k. So I'm going to multiply both sides by, I'm just going to cross multiply really, even though that's probably not the most efficient way of doing this. 8 e to the 7k equal to 31 e to the 3k. And then I'm going to bring my k's to the left. Does it matter which one is the denominator? No, it doesn't. You could have totally done the division the other way, but I made the choice to pick the one with the lower power as the denominator so that when I did the division, the subtraction of powers didn't give me a minus sign in there. But it still would have been fine if there was a minus sign. It would just be one more thing to keep track of. Here I'm going to divide both sides by e to the 3k. So I have 8 e to the 4k equal to 31. And then I'm going to divide both sides by 8. So I'm going to get e to the 4k equal to 31 over 8. Just like we had right there. So it does really get you to the same spot. It's just a different way of getting there. Yeah, these problems always used to kind of throw me off, to be perfectly honest. Like I was like, what do we do? And you have to you can either do this division thing, or you can actually solve each thing for C, set them equal to each other, solve for K first. This is kind of the only type of example where you usually solve for K first, and then go back and plug it into solve for C. Kind of neat. Here's it again, in case you want to see it. Also, just in case you didn't know, right, I hope you all know, but I do post these notes on Canvas after class. I also eventually post the video on Canvas after class. It usually takes me a little while because I have office hours right after this, so I can't do it until after that. Sometimes on Friday, it's a little longer because I don't go back to my office right away, but eventually I will get them posted. All right, so I think that's all the problems on that homework assignment. So hopefully they all make some sense. What it really wants you to circle back around to thinking, though, is that when you're trying to deal with these exponential growth and decay problems, you need to identify the data points, right? You've got a t and a y and a t and a y and either a t or a y, and you're trying to find the other one. Typically, that's usually the setup. All right, what do we got? We got a few minutes left. Let's go ahead and do at least one or two examples of some antiderivatives, because they're definitely going to be the meat of the rest of the class. Or if you don't eat meat, the thing you eat instead of meat, it's totally fine, but I'm going to say the meat because of typical things. So let's say, I'll remind everybody, last time we said the antiderivative of x to a power, and I will say that this is the symbol we're going to use for antiderivative, and maybe later we'll talk about how it's connected to the integral. But the antiderivative of x to a power is x to that power plus 1 divided by that new power plus a constant. And of course, the only power this doesn't work for is -1. Right? The antiderivative of x to the -1 is not x to the 0 divided by 0. That'd be a problem. Just to be super complete about these power rules, or these anti-power rules as I usually call them, the antiderivative of x to the -1 might be easier to think of if you think of it as the antiderivative of 1 over x. So I'm going to be asking this type of question a lot, because this is the way I want you to think about it. If I'm finding the antiderivative of 1 over x, I'm trying to find the function whose derivative is 1 over x. So what function, if you take its derivative, is that equal to 1 over x? Yes, it's the natural log of x. Now, I will also say there's a small caveat here that we're going to address later on, but you should actually know that the antiderivative of 1 over x, the full antiderivative, is the natural log of the absolute value of x. Which is kind of annoying, but it is what it is. So that is what you should think of when you anti-differentiate 1 over x. It's not just the natural log of x, it's actually the natural log of the absolute value of x. We'll address that later, but I want you to know it now so you can stick it in your brain. So now you know how to anti-differentiate any power of x. You just add 1 to the power, divide by the new power. So for example, if we wanted to find the antiderivative of, say, I don't know, x to the 9th plus the square root of x minus 1 over x cubed plus 7, before I start just anti-differentiating willy-nilly, I want to write all these things as x to a power. So instead of writing, so I'm going to rewrite it. I'm not going to do anything other than write the same thing. I'm just simplifying. I'm not doing anything really yet. Instead of writing the square root of x, I'm going to write x to the 1/2. And instead of writing 1 over x cubed, I'm going to write x to the -3rd. 7, You could, if you really wanted to, write 7 times x to the 0. I don't think that's necessary, but you could. Okay, so as a reminder, these two symbols are just instructions. These are instructions that say find, this says find the antiderivative of this function with respect to that variable. So we're going to use the anti-power rule. The antiderivative of x to the 9 is x to the 10 over 10. The antiderivative of x to the 1/2 is x to the 1/2 plus 1 is 3/2 divided by 3/2. Minus, okay, be careful here. People often go the wrong direction. -3 plus 1 is -2, not -4. All right, we have to get less negative if we're adding to it. So we're going to get -3 plus 1 divided by the same power. And here's one that sometimes throws people off. The antiderivative of a constant is that constant times x. The antiderivative of 7 is 7x. How do you know that works? Well, because if you go the other direction, what's the derivative of 7x? 7. And whatever we've got here, its derivative should be what's in there. That's the whole derivative antiderivative relationship. The antiderivative of this is that, the derivative of this is that. In fact, sure. I'm going to write this little picture over here. If we differentiate f to get f prime, we anti-differentiate f prime to get back to f. So if we anti-differentiate f prime to get back to f, we can differentiate f to get back to f prime. What did I forget? Plus c. Now, I will say we should simplify this a little bit because there are two things we can do really easily. Whenever you have x to a fractional power, instead of dividing by that fractional power, we should really multiply by its reciprocal. So I'm going to say this is equal to x to the 10th over 10 plus 2/3 x to the 3/2. And instead of minus x to the -2 over -2, I should really say that's plus x to the -2 over 2 plus 7x plus c. That's how I would write that. Notice also that in the step where I went from the function to its antiderivative, I'm no longer writing the symbol to take the antiderivative because I've done the thing the symbol told me to do. So, yeah. The reason I'm emphasizing that is just because I've seen lots of people over the years keep the symbol there the whole time, even though they've done what it says. So make sure once you've actually done the antiderivative, you no longer need to write the antiderivative symbol or the integral symbol. All right, it's 3 o'clock. We should stop.